Okay, hi, hello. How's it going? This is Ryan here with you, and this is lesson 25 in how to program using Haskell programming language. And this lesson going to talk about other data types, other structures and data types. And one of them, I'm going just to talk about binary search trees. Now, this is something that's usually given in a course or a subject called data structures and algorithms. Okay, it's almost like for the second year, almost. Okay, or a second semester in your studies, however you're taking your degree in the uni. So this is almost like your second month in the semester. You reach that. This is like the most important topic after you learned everything in data structures. Okay. Now, cutting that story short, okay, let's go with what's a binary search tree. Now, binary search tree is when you have data that is ordered, okay, and organized, not just ordered, they are organized in a tree structure like what we see here. Like there's a root node from which the things which are minor to the or lesser in value are to the left, and the bigger ones are onto the right, okay, or they have like a major value, okay, they go to the right, okay, and they recurse. So if you see with me that, for example, here, this one, okay, is a list, okay, is a tree by itself, okay, and when it recurses, so if I want, I can just simply take this and go maybe also this, like, okay, and you can just complete it, okay, with the rest of the branches, okay. So, we think about it as there's one leaf. The tree can be one leaf, okay, or it can be at this corner. See, at the angle, the head of the angle between this leaf and this leaf, okay, at the branching here, can be a branch of a tree to the left and a tree to the right. Cool. Now, this is by concept, but when I apply it to Haskell, you won't imagine how easy it is, okay? It's exactly what I'm talking. There's no pointers, no fuzzy stuff, I don't know from where they came in C or Java, okay? I know it's very hard to program it, okay? It's very long, and I know there are things like related to rotation, things like that, when you delete an item or something like that, okay? Now, what will happen now is we have to go now, I think, with a code. Sorry. So let's go to the code. So when I have a tree, see how easy? We have a tree, and then I have a tree of any type, okay? It should be like a list. In a Haskell list, everything has to be of the same data type. Okay, if everything in the list is integer, every element in the list has to be an integer. You cannot make a mix. Otherwise, you'd better use a list of tuples. Okay, but everything has to be consistent in regarding the data type. So it can be a leaf, A, or it can be a branch of a tree of the same type and another tree of the same type. Now, what does this mean? This means that I'm calling the tree back. So another time you're calling or you're building a tree, okay, it has to be a leaf or a branch, okay, and it recurses and repeats, okay, and goes down and down in the list, okay, of this tree, okay, or in the structure of this tree. Now, we have to think about it as if that the tree of A, this is the left side of the tree, okay, and this is the left side, the right side of the tree, okay. So this is between us, left, and this is right. Cool, and it recurses all the time. Now, This is the definition of the map of a list. Now what we're going to do is apply this to a tree. Okay, so if I'm talking about a list, okay, and I want to do mapping over it, so everything has to everything in the list has to be turned or applied to a function, okay, one by one, element by element, okay, to get a new list. Like for example, multiplying the whole list with the number 2. Every element of the list has to be multiplied or doubled. Okay, so by definition the mapping is anything or whatever the function is with an empty list, okay, gives me that empty list. Of course, there's nothing to do. Now if I have a function that has to do me something, okay, then what we'll do is apply the element, the first element, with the f. So this is how I get, okay, and then I concept with the rest of the application of the rest of the list on the function f to do me mapping. Cool. So this way I can go one by one to in that list and apply that function because of the recursion. Okay, I'm not gonna repeat the lesson of recursion. You have should have seen it. Now let's see how in the mapping it will go. Okay, now if I say I have a function called tree map, okay, now if I want to apply a function of a to give me b, a function of signature of some type a to give me another value, single value of whatever that type is, okay, of that value b, and take a tree, okay, starting with a, okay, it should give me another tree with another value of b, okay, which is which that b is given by the function of a to give me b. Okay, now I think this is redundant. Okay, anyway, tree map of f, so I'm applying f to the tree. So the tree can be what? Can be applied to a leaf or can be applied to a branch. Okay, how easy is that? Just to multiply or map the whole list in the tree. Okay, because also I have to remind you that a list itself, that's why they're using the same idea of the list. The list itself, if we want, we can just join, for example, those under the red line, okay, which are rounded with the black circle. Okay, those can be one list. So if a tree has to go minimal and stay a tree like, it is a list. Okay, of course I'm not talking about just single node, I'm talking about like if there are so many elements. Okay, now so if I take a leaf, I take its value x, the thing that is in the for example, if we look at the green circle as if it's the plate and there's the thing that's inside it, whichever that thing. So this is the thing that's whichever there is represented by x. Okay, so I take that thing inside that plate and apply it to f. Okay, now to get the new content of the leaf, or to get the new content of that plate, if we want to say, I put what? F of x, and this way I get this part to give me a tree, but this is a tree made of just only the leaf side of the data type. Now let's go for the branch side of the data type. Okay, so I'll take a branch of left and right. So what will I have is, of course, the branch itself by itself, okay, is not something like that we deal with like as a word it's by itself. This is just the name of the constructor. We don't deal with the name of the constructor, we deal with the values that are applied by the constructor. So I take f and apply it back again to the tree map of the left side, and similarly with the tree map of the right side. And we know that what we want to do is map should give me a tree. Okay, similarly to a normal list, it should give me a list. Okay, so this is how it's made. Okay, so by calling back tree map again, I can go deeper in the tree map, the tree, and it will recurse and so on to be, for example, multiplying everything by 2 inside that tree. Cool? Now, how do we fold right or fold a tree? No, fold right, this is just for the list. So we're going to mimic that and apply it to the tree. Okay, now there is no fold right or left like in the list. Okay, so what will happen is I take the function, and we know the folding has to like zip up everything, if you want to say, or compress everything, or wrap everything into just one number. You won't see a data type called tree. Okay, similar to the folding in fold right or fold left, everything has to be compressed and condensed into one type that's not something like tree, something like integer, something, you know. It has to go to the primitive type. Okay, so I'm just revising with you here the data type fold right. So fold right of f of z, okay, on also list which is empty. Okay, it should give me only z, because the empty list, you cannot do anything with it, and the z is just something to stop the recursion. Okay, there's some point that the folding should stop. Okay, because we can't go all the way like in the next step here in the recursion. You can't just go, for example, f of x of the fold right of f of z and the rest of the list that's submitted by here. Okay, we cannot go further and further if we don't put this. Okay, anyway, so it's understood that I have to fold everything using fold right. Now this is how we do it in tree fold. I know you have been reading, but we have to read it for those who did not understand how it goes. Okay, so tree fold, what will it do? It will take a function of 2 parameters, okay, to give me a value, okay, by which this function is applied. It takes another, function, okay, and a to give me b, okay, and also takes a tree to give me at in the end another value of the type of b. Okay, so we take the function has to be applied on the branch and also has to be applied on the leaf. You cannot just work it on only one on the leaves and without talking about the branch, because you're folding by the definition of the data type, you're folding on a leaf and you're folding on a branch. Okay, that's why I have to make 2 functions that should work on both types. Okay, so it's g, okay, where g, it's another function g, where g is a function that applies on the leaf side, and this is the g also is applied on a branch side of the data type. Okay, so I take f leaf of x, okay, and also so I apply f of leaf of x on when it's leaf, and also I apply the branch. Okay, once I take a tree of that's named left, another tree also named right, okay, then I apply the branch, okay, on the g of the left and the g of the right, okay, because you will have to recurse. Okay, so finally you'll find yourself when it recurses, because you're talking about another tree here in the g, okay, because you want to go deeper, and dig deeper into in the tree into more lower levels, which I'm talking by, this is the lowest level here you're talking about, or the deepest level. Okay. Imagine that this is like a directory structure, for example. Okay, this is a tree also. So this way, okay, everything will go back to g of leaf of x, where it is equals to f of leaf of x. Okay, so if left and right are now just normal numbers, okay, you will find yourself computing this. Cool. Now, this is how we define a tree. Okay, like just to instantiate a one. Okay, to start with a tree variable. So a tree of integers is made as such. Okay, you have to start with a branch and define the left side and the right side. Okay, like something like, if you want to see a tree 2, okay, equals branch of 2 and 1. This is basically it, what it should be. But later, if you want to go further, you have to say another branch, okay, which should take 1 and 2, okay, and also another branch which should take 3 and 4. Okay, and so on and so on and so on. So if we looked here, finally we should find ourselves in a branch where it is just 2 leaves. Okay, oh, so yes, here should be another branch of a leaf, because you cannot just put it like this. A leaf of 1 and a leaf of 2, and similarly here, let me copy this. Okay, so that's it. That's all about the lesson. Okay, thanks for watching. Please subscribe to my channel so you can get updates and newer lessons. Okay, and don't forget to click the ads and click the likes. Thanks for watching.